Okay, so here we have a ball of mass m being released from a vertical height h from rest, so v initial is 0, and the ball rolls down the incline and then goes through this loop. So this is a circular motion problem, and we're given the radius of the loop as r. Now this problem is all in terms of variables, so you'll notice in the question up here it says derive an expression. So an expression, what that means is the answer will be not numeric. It's going to be in terms of these variables. M for mass, r is the radius of the loop, h is this starting vertical height of the ball, and then g is gravity. All right, so the first question is really not a circular motion question. It's actually a conservation of energy question. So the way we go about solving number 1, which is asking for the velocity of the ball when it reaches the bottom of the incline. So we'll put the ball down here. So the ball is going to go faster, 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 faster down the hill. And when the ball reaches the bottom, what is the velocity? So this is conservation of energy. Whenever you do conservation of energy, you need to have a 0 point. So we'll just go ahead and put in the 0 point in red. So this bottom here, this is going to be our 0 point right there. That's the lowest point in the problem, the best place to put the 0 point. Okay, so with that as our 0 point, so we're going to say potential energy initial plus kinetic initial equals potential energy final plus kinetic energy final. And there's no non-conservative forces here. The only force doing work on the ball as it goes down the incline is gravity, so I'm not even going to mention work non-conservative up here. We do have potential energy initial. The ball starts above the 0 point. There is no kinetic energy initial because the ball starts at rest. Then the ball goes down the hill. Down here is our final. There is no potential energy final because the ball's on the 0 point, and we do end with kinetic. So potential energy initial equals kinetic energy final. So potential energy is mgh. Kinetic energy is 1/2 mv squared. M's cancel, and we can solve for v, which comes out as the square root of 2gh, which is the answer to number 1. All right, now second question, we're getting into circular motion here. So if we look at the ball at the lowest point, let me erase this here. So here's the ball as it passes through the lowest point. The forces on the ball are mg down and normal force up. Those are the two forces that are acting on the ball. And we're being asked to solve for the normal force. What's the normal force on the ball when the ball is at the lowest point of the loop, when it reaches the bottom of the incline? Now the normal force and mg are not going to be equal because the ball is now in a circular path. The normal force is larger than mg, and the way to understand that is a split second later, when the ball is right here, it's moved upward. It's now in a circular path, which means that there's a centripetal acceleration. All objects in a circular path have a centripetal acceleration which points to the center of the circle. So here's the center of the circle. And because the centripetal acceleration always points to the center of the circle, we always want to make the center of the circle positive. So for the ball here, we're going to be saying up is plus, and down is minus. The center of the circle is positive. Okay, so now what we do, there's our free body diagram. What we do now is we sum the forces for the ball at the lowest point here, and we have normal force up and mg down, and the sum of the forces equals ma. And because the ball is now in a circular path, this acceleration is a centripetal acceleration. And we know that centripetal acceleration is equal to v squared over r. So we can take that plug it in there. So now what we have is normal force minus mg equals mv squared over r, and we're solving for the normal force. So the normal force is going to be mv squared over r plus mg. Now we'll notice that v is not allowed in our answer. If you look up here, we can only use m, r, h, and g, so we need to get rid of the v, and the way we do that is by plugging in the velocity at the lowest point. So we can plug that in right here, because we've already found the velocity at the lowest point. So writing the whole thing out again, this will be normal force equals m square root 2gh squared, so that square root's going to disappear, over r plus mg, which is going to give 2 mgh over r plus mg, and then so that would be an acceptable answer. But to clean this up a little bit, we could say normal force. I'm going to factor out the mg. So this will be mg times 2gh over r plus 1. Oh wait, that g should not be there. Oops. Erase that g. Okay, that's the answer. Okay, normal force equals mg parenthesis 2h over r plus 1. All right, now the third question, find the minimum velocity the ball must have at the top of the loop in order to not fall out of the circular path. So we're going to clean this up, make some room here. All right, so now we're focusing on the ball at the top of the loop. So I'm going to put the ball up here. As the ball passes through the top of the loop, the forces on the ball, we have mg down. Mg is always down. And then the loop is pushing the ball down also. That's a normal force. You know, you got to realize here that this track is simply a surface, and as the ball rolls through the top, the surface is pushing down on the ball. So the key thing here is the minimum velocity at the top of the loop in order for the ball to not fall out. So if this ball goes through the loop real fast, there's no danger of the ball falling out of the loop. But as the ball goes slower and slower and slower, so say you send the ball through the loop 100 times, and each time the ball goes through slower and slower and slower, what happens is the track pushes with less force on the ball as the ball slows down, until finally the normal force goes to 0. So the key thing here is that when the ball barely makes it through this loop, the normal force goes to 0. So I'm just going to erase this normal force. When the ball barely makes it through the loop, the only force acting down on the ball is mg. Or another way to look at it is you could set the normal force, keep it there, and set it equal to 0.0000000001. So the normal force is barely there, but for all practical purposes, the normal force just goes to 0. So for number 3, we sum the forces. And remember, for circular motion problems, we want the center of the circle to be positive. And again, the reason for that is the acceleration, the centripetal acceleration of an object in a circular path always points to the center of the circle. So we want the acceleration to be positive. So summing the forces here, mg will be positive because that points to the center. And that's the only force on the object, on the ball, because we're setting the normal force equal to 0. Or you know what we could do is just put normal force in here, put it back there. So we'll say mg plus normal force equals ma, where that's a centripetal. But like we said, if the ball barely makes it through, the normal force goes to 0. So what we're left with is mg equals mac, and we know that centripetal acceleration is v squared over r, so we plug that in right here. So now we have mg equals mv squared over r. The m cancels, and we get velocity equals square root gr, which is the minimum velocity in order for the ball to make it through the top of the loop. And then the last question, what's the minimum vertical height that the ball must start with in order to barely make it through the loop? So we have the velocity at the top of the loop, the velocity for the ball to barely make it, square root gr. So now what we do is we do conservation of energy using over here as the initial and here as the final. So the initial is there, the final is there. So conservation of energy, potential initial plus kinetic initial equals potential final plus kinetic final. Okay, so potential energy initial, we have it. The ball starts above the 0 point. Kinetic initial, we do not have it because the ball starts at rest. Over here, up at the top of the loop is our final. We do have potential energy because the ball is above the 0 point, and we do have kinetic energy because the ball is in motion. So potential energy initial is going to be mgh. Potential energy final is going to be mg. Now the vertical height of the ball here is double the radius. It's the diameter of the loop, which is 2r. So I'm going to plug that in for h. That's the final vertical height, mg, and then the h here is 2r plus 1/2 mv squared, and this is our velocity. We're going to be plugging that in right there. So all the m's cancel. The m's drop out. So now we're left with gh. Oops, this m cancels too. Gh equals 2gr plus, now I'm going to plug in for v here. This is going to be square root gr squared over 2. So writing it out again, gh equals 2gr plus gr over 2. The g's drop out, and then h comes out as being 2.5 r.